We're always trying to build bigger, better, stronger, right? And a huge part of that comes down to these incredible materials, like super strong steel. But what if the very thing we do to put them together actually creates a secret flaw? All right, let's just jump right in. Think about it. We use welding for, well, everything. Skyscrapers, ships, you name it. But it all boils down to one really critical question. What happens when the thing holding two super strong pieces of metal together isn't so super itself? So, first things first, what exactly are we talking about here? It's called ultra-high strength steel, or UHSS for short. Now, according to the source material for this explainer, the technical definition is steel with a yield stress over 690 megapascals. What that really means, in simple terms, is that it can take a massive amount of force before it even starts to bend. And that's huge, right? It lets engineers build things that are way lighter and more efficient. And that brings us to the big paradox we're going to dig into today. Section 1, stronger steel, weaker welds. Okay, so here's the deal. The heat from a welding torch, it's just so incredibly intense. It's so hot that it can actually change the internal structure of the steel right next to the weld itself. You think you're joining two super strong pieces, but what you might actually be doing is baking a hidden weak spot right into the metal, and that could compromise the whole thing. All right, let's move on to section 2. We're going to zoom way in, down to the microscopic level, kind of like a crime scene, where this weakness actually gets created. We're talking about the heat-affected zone. Now, this definition is super important. The heat-affected zone, or haze as you'll see it called, it's not the weld itself, not the part that actually melted. No, it's the tiny sliver of steel right next to the weld that got, well, cooked. It got incredibly hot, but it didn't melt. I love the analogy they use. It's like the scorched ground around a campfire. It wasn't actually on fire, but the heat changed it completely. And believe me, that change can be really, really bad news. The research paper we're looking at lists a bunch of potential problems here. Things like cold cracking, a major drop in the joint's strength, loss of ductility, that's its ability to bend instead of just snapping, and lower fracture toughness. For an engineer, these are all giant red flags. So, okay, you've got this microscopic problem, and it's created in a flash of insane heat. How in the world do you even begin to study that? Well, that brings us to section 3, simulating the perfect weld. This was the big challenge for the scientists here. I mean, how do you grab and test a tiny little zone that's been totally transformed by this quick, violent blast of heat from a weld? You can't just cut it out of a finished weld, right? The results would be all over the place. The solution? It's this absolutely brilliant machine called the Gleeble 3800. What it is a thermomechanical simulator. Basically, it can take a tiny, perfect sample of steel and put it through the exact same heating and cooling cycle it would go through if it were sitting right next to a real weld. It's amazing. It lets them create a perfect sample of just the heat-affected zone, ready for testing. So here's the game plan broken down into 4 simple steps. Step 1, they prepped these little samples of steel. Step 2, they used that Gleeble machine to simulate the welding heat. Step 3, they took these newly created samples and tested their mechanical properties. And finally, step 4, they put them under the microscope to figure out why all these changes were happening. And you can see here, they had to machine these samples into some pretty specific shapes to test them properly. The one on the left, that's the dog bone shape. They use that for tensile tests. They literally just pull it apart from both ends until it snaps to see how strong it is. And the one on the right with the little notch, that's for impact testing. They smack it with a pendulum to see how it handles a sudden, sharp impact. All right, so the stage is set. The samples are ready to go. Time for the main event. Let's head into section 4 and see the results, which really turned into a tale of 2 very, very different steels. So the 2 contenders in this test were 2 different grades of this super steel, S960 and S1100. And it turns out the key difference between them was how they were made in the first place. The S960 steel was made using a process called direct quenching, which is basically just a super fast cooling process. But the S1100, it was made with quenching and tempering, which adds an extra step. They reheat the steel after it cools to get rid of internal stresses. And as we're about to see, that one extra step made all the difference. Let's start with the S960 steel. The results were pretty shocking. In the weakest spot of its heat-affected zone, the hardness dropped by a whopping 29%. That's almost a third of its hardness, just gone. A massive, massive loss. And this graph from the study just lays it out so clearly. The red line, that's the S960 steel. See that huge V-shaped dip? That's the scary part. That's the dangerous softening happening in that heat-affected zone. Now look at the black line for the S1100 steel. Wow, it's just so much more stable. No catastrophic drop whatsoever. And this next chart? This shows you that the loss in hardness isn't just some abstract number. It translates directly to a loss of strength. These are called stress-strain curves. If you look at the S960 on the left, you can see how the curves for the heat-affected samples drop way, way below the line for the original steel. I mean, they just got a whole lot weaker. And this table just sums it all up perfectly. The S960 steel, it lost a staggering 32% of its strength in that weak zone. 32%. But the S1100 steel, it lost just 2%. The difference here? It's not even close. It's night and day. So, what does all this lab data actually mean for building things in the real world? Well, let's get into that in our final section, Building a Stronger Future. And get this, there's a really cool twist here. The S1100 steel didn't just avoid getting weaker. In some places, it actually got stronger. The paper points out that parts of its heat-affected zone actually hardened, increasing by as much as 13%. So for this steel, the welding process actually made it better in some spots. How crazy is that? And this right here is why this research is so important. This isn't just for academics. Knowing that the manufacturing process, direct quenched versus quenched and tempered, has such a huge impact on how strong a weld will be, that's absolutely critical information for any engineer trying to pick the right material for the job. It's about building things that are safer and more reliable for all of us. So let's just do a quick recap of the big takeaways here. Number 1, not all super steels are the same, not by a long shot. Number 2, how a steel is made in the first place completely changes how it reacts to being welded. And number 3, at least in this study, the quenched and tempered steel, the S1000, was just way, way tougher against weld heat than the direct quenched S960 steel was. And that really leaves us with one last big question to think about. As we keep pushing the limits with all these amazing new materials, are we actually asking the right questions? Are we looking hard enough for the hidden weaknesses that might be staring us right in the face?